Okay, so picking up where it got cut off, this means that both are at the same temperature. So the energy absorbed by the cooler object is going to perfectly equal the energy released by the hotter substance. So if we use their Q values, knowing that we just finished calculating using the equation Q equals mc delta T, if I set Q of each one, bless you, equal to one another, then I would get my mass times my specific heat times my temperature change of one thing is equal to the mass times the specific heat times the temperature change, bless you, of the second thing. So I'm going to write, for the hot object, my negative mc delta T is equal to my positive mc delta T of the cooler one. And again, the only reason that this is negative is because that is showing that energy or heat is being released by that object, and this one is positive because it is the one gaining the heat. So if it makes more sense to you to think of it as a more like just numbers only thing, and then add the concept of where the heat is being transferred at the end, that's totally fine with me. The other thing that you can do is, if the negative throws you off, I sometimes will show students that you'll put a -1. I don't know why I wrote it so small. So treat it like it's being multiplied by a -1, and that's totally fine as well. That sometimes helps mathematically. If what you should calculate if you're losing heat is that you're going to have a negative temperature change, and then that makes everything end up being positive. So let's talk about this in terms of an actual example, and then I think it starts to make more sense. So example 1 says a piece of metal weighing 59.047 grams was heated to 100 degrees Celsius, and then they put it into a 100.0 milliliter thing of water. The water was initially at this temperature, and then the metal and water were allowed to come to an equilibrium temperature determined to be this. Assuming that no heat was lost to the environment, calculate the specific heat of the metal. So let's start by drawing like a little picture of what's happening. First, I've got this container. We can call it a beaker if we want. In real life, what we're going to use with this is what I call a calorimeter. And so I'll actually just zoom this out so you can see what I'm talking about. I use styrofoam cups because they tend to hold heat really well. So this would be the bottom sitting on your table. Zoom it out as much as I can. And then I take an inverted styrofoam cup and put that on the top. So you've got this here. And then that creates basically a seal. And then how we'll take the temperature is by sticking a temperature probe into the hole on the top. So if I take my temperature probe, put that in there, I can take the temperature of whatever's happening in here. What this does is it holds heat really well. So styrofoam as a material is designed to not let a lot of heat escape. And so by having styrofoam enclose all of this, it's not losing heat to the environment. Whereas if this were to actually take place in a beaker, a lot of the heat from whatever your hot object is would not be able to be measured in our lab setup because it'd be released to the environment, and we have no way to measure. Like, it's not going to release so much heat that it's actually changing the temperature of the classroom or something like that. So this is kind of our like little makeshift calorimeter. So in our lab, we have a couple of different labs that we do with this. Your calorimeter is referring to this setup right here. So you'll have the styrofoam cup with a cutout styrofoam cup on top, inverted with a hole for your thermometer. And ideally your hole is like as small as possible because then you just have enough space to fit the thermometer in there, and that's it. Make sense? So that's kind of what this setup is supposed to be using, but just for the sake of drawing it, I'm going to do it in a beaker. And then what we have is initially how much water is in this beaker, or in this setup. 100 milliliters. So I'm going to draw 100 milliliters right there and say that is the level of my water level. That's how much water is in there. So I have 100 milliliters of water, and then inside of that I have a piece of metal that weighs this much and heated to 100 degrees Celsius. So that is my hot metal is in here, and it's 100 degrees Celsius. The rest of the water initially was at 23.7 degrees Celsius, making it my cooler substance or my cooler object. What this tells me is that when I put that hot metal into my cooler water, that metal is going to start losing heat to the water. The water is going to then heat up in response to this, and the metal is going to cool down. So you have two things going on at once. The metal is my hot object that is releasing heat. That's why it has a negative value. And the water is my cooler substance that is absorbing heat from the metal. Make sense? Then at the end, once they have reached thermal equilibrium, my final temperature of both of them, so once they stop changing, eventually they reached my thermal equilibrium temperature, which is determined to be 27.8 degrees Celsius. So that at the end, both are 27.8 degrees Celsius. So these temperatures that are given here, I would consider my initial temperature of my metal substance and my initial temperature of the water. So if we assume that all of the heat has been captured in this and all of it is accounted for, we can calculate the specific heat of the metal, which means we are calculating a C value, and then we can use that information to determine what the metal actually is. So I'm going to just follow this setup right here and go straight across, where I'm going to use my -1. So for my hot substance, meaning my metal, put the -1 there. All that is telling me is that this is going to be negative, or it's going to be multiplied by a negative because that heat is being released, because it is being lost. My M is my mass of the hot object, so that's going to be 59.047. And then my delta T is the temperature change of my hot object. My hot object started at 100 degrees, so delta T for the hot object. The final temperature was this, so 27.8 degrees Celsius minus 100 degrees Celsius. If you can't do it in your head, always use a calculator. So 27.8 minus 100 gives me negative 72.2. So I'm going to plug in negative 72.2. So by showing me that I'm multiplying it by a -1 because I'm releasing that energy, what that does is I'm effectively multiplying a negative by another negative. So that gets rid of the negative value, which means that you're actually able to get a positive value on that side. So at that point, you can cancel out your negatives, if that makes sense to you. And then you're multiplying, by your C value as well. Because your specific heat, your C value, will always be a positive number. Two ways you can tell that. One is by if you look at your specific heat chart, which is right here, none of your values are negative. And also, by definition, the specific heat is how much energy it takes to raise the temperature of something, and nothing is going to take a negative amount of energy to raise the temperature. It's always going to take some kind of energy put in to raise the temperature of it. So for my hot substance, those are all the numbers that I would need to use in my calculation. And then for my cool substance, my water in this case, I have a volume of water given to me, 100.0 milliliters. And I know, because I memorized it back during Unit 1, that the density of water is equal to what?
What'd you say?
What is the density of water? One what? 1 gram per milliliter. So I know that because of the density of water, since my cool substance is water and my density of water is 1.0 grams per milliliter, that if I have 100 milliliters of water, how many grams of water do I have? 100. So I can use my volume of water as my mass of water because it's the same thing for that specific substance. So I'm going to use 100 as my mass of water. times my C value, which is the specific heat of water. On the other page, it tells me that's 4.184 for liquid water. And then my delta T value. So delta T for water is going to be 27.8. That's my final temperature minus my initial temperature of 23.7. If you can't do it in your head, plug it into your calculator. So 4.1 degrees Celsius. And it's positive because it's absorbing that energy. So 4.1 here. So with all of these numbers, I can set it up and solve for the C of my hot object, or of my metal. So just like before, I need to divide by everything that's being attached to it. So I would divide by -1, divide by 59.047, and divide by -72.2. 72.2 parentheses, okay. So the negative and the negative would cancel. We're good. Divide by 59.047. So then I would divide this by the same thing.